Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 5 of this NPTEL online certification course on bioreactors. In the last lecture, we saw that the two major products from a bioreactor could be the cells themselves or the products that are produced by the cell. We said at that time. We will refine it a little better in this lecture. We also saw the various models for the variation of specific growth rate with substrate concentration, with product concentration, and essentially the models for the growth kinetics. And we also saw the model, the Ludeking-Puré model for the product formation kinetics. Then we saw a few concepts such as the yield coefficient, the maintenance, and that is where we finished up in the last lecture. Let us begin this lecture with enzymes. We said we will slightly improve the outcomes from the bioreactor, cells themselves and the products that are made. Earlier we said that the products that were made by the cells, it could also be the products that result from an enzyme mediated reaction. All of you would have heard of enzymes. Enzymes, usually proteins, which are produced by microorganisms in bioreactors, are used extensively in the industry. And that is the interest in the enzymes themselves. Then the enzymes could mediate products from, let's say, from A to B conversion and so on and so forth. The B could be the preferred product over A, and the transformation through enzymes, the biotransformation through enzymes, could be carried out in a bioreactor. But before we look at that, let us look at enzymes themselves. These are produced by microorganisms and are extensively used in the industry. I have given a few examples here, and this use has been for a few decades now. The listing is as enzyme industry and the enzymes used. They are heavily used in the detergent industry, especially enzymes such as proteases and amylases are used in the detergent industry to improve the cleaning ability of the detergents. In the baking industry, amylases are used. In the brewing industry, amylases, glucanases and proteases are used. In the dairy industry, rennin, lipases, lactases. In the starch industry, amylases, glucose isomerase. Remember, we said that starch can be broken down to glucose for further fermentation. Amylases are the ones that could carry that out. Textile industry, amylase. Leather industry, trypsin, proteases, and cocktails of enzymes could be used. Mixtures of enzymes could be used in the leather industry. Pharmaceuticals, trypsin, and that is just examples of the use of enzymes in the industry. As was mentioned previously, enzymes can be used in the bioreactors as the agents that cause different products to form. And there is a special name for that bioreactor. Such bioreactors are called enzyme bioreactors. Examples here: penicillin acylase for 6-amino-penicillanic acid or 6-APA production from penicillin G. Penicillin G is converted to 6-APA through penicillin acylase. 6-APA is widely used, and glucose isomerase is used to produce sweet invert sugar. This is also used heavily in the industry, in the food industry, beverage industry. And as before, we need to have a good understanding of the kinetics of the enzyme reaction. Earlier we looked at the kinetics, the rates of growth and the rates of product formation. Here we need to have a good understanding of the kinetics or the rates of enzyme reaction, and they become essential in the design and operation of enzyme bioreactors. So we will look at enzyme kinetics predominantly in this particular lecture. Let us make things as simple as possible. Let us see how an enzyme reacts to form the products, or how the product is made in the presence of an enzyme, how the enzyme mediates the process, how does it get involved in the process. One of the simplest mechanisms that have wide acceptance for simple enzymatic reactions is as follows. If E is the enzyme which converts substrate S to product P, the mechanism that is considered here is the enzyme reacts with the substrate in a reversible fashion. The rate of the forward reaction is K1, the backward reaction here is K2. This is a reversible reaction to form an enzyme substrate complex, and this reaction is fast, and it's also an equilibrium reaction. The K1 is rather high, the equilibrium reaction, and then this enzyme substrate complex reacts further, converts further to enzyme and product. This is through the rate constant here is K3. This is the overall mechanism of simple enzyme mediated reaction. If this is the case, and let us say this is occurring inside a closed vessel, a batch reactor, which we take as a system, if we write a mass balance on the product, we are going to focus on the product and write a mass balance for the product, that gives the rate of generation of the product that is given here minus the rate of consumption. Remember, this is a batch reaction, and therefore the input and output terms are 0. The input and output rates are 0. So those two terms disappear, and we have only the generation and consumption terms associated with the product. So the rate of generation minus the rate of consumption of the product equals the rate of accumulation of the product, all this in mass terms. There is no, if we assume that there is no consumption of the product, then the rate of generation of the product equals the rate of accumulation of the product here, rate of generation, rate of accumulation. And we know from chemical kinetics that the rate on a per unit volume basis, the volumetric rate as we call, is RGP per unit volume. Okay, this is the normal way in which we write our rates on a per unit volume basis. This rate is on a mass basis, mass per time. This is mass per volume per time. This is what you'd have learnt in your high school, high secondary school, and so on. The rate on a per unit volume basis is K3 into the concentration of the enzyme substrate complex, first order kind of a thing there. That was the earlier equation. So to get to the value of interest to us, which is mass per time, we need to multiply both sides by the volume of the system. Because this is on a volumetric basis, we are looking for a mass basis. Concentration is nothing but mass per volume. If we multiply that, then we get rate on a mass basis, the rate of product generation on a mass basis. Let us call it Rp for simplicity, equals K3 into the concentration of the enzyme substrate complex into the volume V. Now let us write a mass balance on the enzyme in the vessel. Earlier we wrote a mass balance on the product. Now let us write a mass balance on the enzyme. If we do that at any time of interest, the enzyme is either free or bound to the enzyme substrate complex, as we had viewed in our mechanism. Therefore, the mass of the total enzyme ET is the concentration of the total enzyme times the volume. The mass of the total enzyme is the mass of the free enzyme plus the mass of the enzyme that is bound to the enzyme substrate complex, right? Therefore, the mass of the free enzyme is concentration of the free enzyme into the volume, the same volume as this, plus the mass of the enzyme that is associated with the enzyme substrate complex is the concentration of the enzyme substrate complex times the volume. So, this is just the mass balance. This is what can be equated, right? The concentrations cannot, since the concentrations cannot be equated directly, but the masses can be equated. Now, since all the volumes are the same, we get equality in concentrations. The concentration of the total enzyme equals the concentration of the free enzyme plus the concentration of the bound enzyme, or bound as enzyme substrate complex. And therefore, this is just transposition of this equation. The concentration of the enzyme substrate complex is total concentration of the enzyme minus the concentration of the free enzyme. Now, if we plot the concentrations of, let's say, the substrate, the product, and the enzyme substrate concentration versus time as the reaction proceeds, it will be something like this. The substrate is going to react to give the product, therefore, that goes down. The product is going to get formed, therefore, that keeps going up. And the enzyme substrate complex behaves something like this. At very small times, there is an increase, and then there is no change in the concentration of the enzyme substrate complex. Okay. So, apart from very short times here, early times, the concentration of the enzyme substrate complex does not change. Therefore, if we are interested in this region, this range of times, then we could say that the accumulation rate of the enzyme substrate complex is 0, because if it is accumulating, it should either go down, it should either go up or go down. That's not happening here, and therefore, this can be put as equal to 0. This is the same equation as earlier. Generation rate of enzyme substrate complex minus the consumption rate of enzyme substrate complex from the material balance equals the accumulation rate of the mass of enzyme substrate in the system, and since there is no change in concentration, that goes to 0. Now, this is what you might have seen if you remember your enzyme kinetics from high school or your pre-engineering preparations and so on and so forth. This is only a limited way of looking at this concept. In fact, this concept is very powerful. So, let us look at a generalized way of the consequences of this particular aspect. Okay, to do that, let us consider an example. Before I say that, I should also say that the concentration here does not change, therefore, this rate is 0. Therefore, you can assume or take the enzyme substrate complex to be at pseudo steady state. That's what PSS means, pseudo steady state. Okay, this concept is fine in the case of a batch system. Let us generalize that concept. To generalize that concept, let us consider an example, a fictitious example, of making an engine for a car. Let us say that we are putting the engine together in-house, right from the bolt to the engine. The time that is needed for the manufacture of a bolt is on the average about 5 seconds. Let us say that. Okay. And let us say that the time on the average for the manufacture of an engine is about an hour. This is an average of 5 seconds. It could be 6 seconds, 7 seconds, 3 seconds, 4 seconds, whatever it is, or even 2 seconds and so on. It could vary, right? And that is the unsteady aspect in the manufacture of the bolt. Whether it takes 5 seconds to manufacture a bolt, or 7 seconds to manufacture a bolt, or 3 seconds to manufacture a bolt, has no impact on the time that it takes to build an engine. This is of the order of an hour. This variation in a matter of seconds is not going to affect the rate at which the engine is being made. The unsteady nature, the time varying nature of bolt manufacture does not affect the kinetics of engine manufacture. That is because these two are widely separated in terms of their characteristic times, as they are called. This one is in a matter of seconds you manufacture this one takes thousands of seconds, 60 into 60, about an hour, 3600 seconds. So if the characteristic times are widely different, the unsteady nature of the faster process does not affect the kinetics of the slower process if our interest happens to be in the slower process. So while looking at the slower process, we can always consider the faster process or a much faster process to be at pseudo steady state. In actuality it could vary, but that variation does not affect the process, the slower process. So the faster process in comparison can be taken to be at pseudo steady state. And this is a concept that has wide applications. You can also look at it this way: the enzyme substrate complex formation variation is very fast compared to the times over which the product gets formed, and therefore the enzyme substrate complex could be assumed to be at pseudo steady state compared to the product. So whenever we use the pseudo steady state assumption, we need two processes which are widely separated in terms of the characteristic times. We'll visit this later, but for now, whichever way you understand it, it's fine. It's not going to affect the understanding of the derivation of the kinetic equation. Okay, let's go back to this. We had enzyme plus substrate giving you reversibly an enzyme substrate complex and irreversibly an enzyme and the product. The rate of generation of the enzyme substrate complex, we're going to focus here, is nothing but K1 into the concentrations of enzyme and substrate into the volume. This is on a volumetric basis, this is on a mass basis, therefore we need to multiply it by the volume. And the rate of consumption of the enzyme substrate complex, as you see here, it is consumed through the reverse reaction with the rate constant K2 and this reaction with a rate constant K3. The consumption is K2 into concentration of the enzyme substrate into the volume plus the K3 into the concentration of the enzyme substrate complex into the volume here. So this is the rate of generation, rate of consumption, and so the mass balance turns out that the rate of generation minus the rate of consumption, rate of accumulation is 0. This is what we have already seen as the pseudo steady state assumption, and therefore the rate of generation of the enzyme substrate complex equals the rate of consumption of the enzyme substrate complex, because this is equal to 0 in the previous step. Replacing the rates by the concentrations, K1 into E into S, both are concentrations into volume, equals K2 into enzyme substrate complex concentration into volume plus K3 into enzyme substrate complex concentration into volume. The volumes are the same, therefore they can be cancelled, and therefore you get K1 into E into S equals K2 into ES plus K3 into ES. That's the same equation, and we are just transposing this. We are collecting all the K1 into E. E is difficult to know, whereas ET we can have a handle on. Therefore, let us write E in terms of ET and the enzyme substrate complex. We had derived this earlier through a mass balance on the enzyme. You can go back and check that. K1 into ET minus E enzyme substrate complex into this S. This is common here, therefore K2 plus K3 into ES. and a little more of algebra. I'm just taking this S inside the bracket, and then I'm combining the terms which have the enzyme substrate complex. So K2 into K3 into enzyme substrate complex plus K1 into enzyme substrate complex into S, and therefore you could write this as the left hand side remains the same, the right hand side, if you take the enzyme substrate complex concentration common out, K2 plus K3 from here plus K1 into enzyme substrate K1 into S, the enzyme substrate complex is out, therefore K1 into S here, and therefore the concentration of the enzyme substrate complex is the left hand side divided by the factor here, K2 plus K3 plus K1 times S. And if we divide the numerator and the denominator by K1, right, we get the K1 disappears from here, so ET into S, and here K2 plus K3 divided by K1 plus S. There's a K1 here which gets cancelled, plus S equals the enzyme substrate complex concentration, which is the same as this. And if I call K2 plus K3 by K1 as some capital Km, then the same equation can be written as this: ETS divided by Km plus S equals enzyme substrate complex concentration. And we had earlier seen that the rate of product formation in terms of a mass rate is K3 into ES into the volume. You can go back and check that equation. So if you substitute the enzyme substrate complex concentration from above, we get the rate of product formation is K3 into ETS by Km plus S in the place of enzyme substrate complex concentration times V. And if I say K3 into ET, K3 into the enzyme total enzyme concentration, if I call that as Vm, Rp becomes Vms by Km plus S into V. Note that Rp is on a mass basis. Rp on a per unit volume basis, on a concentration basis, let us call that as V to be consistent with the terminology that you would be familiar with. So V equals Vms by Km plus S. Does this appear familiar? Of course it does. This is the well-known Michaelis-Menten equation. Okay. This is the simplest enzyme kinetics equation for a single enzyme, single substrate case, which goes as enzyme and substrate reacting together in a reversible fashion to form the enzyme substrate complex, which further goes to give you the product and the enzyme back. So this is V equals Vms by Ks plus S. Does this form of the equation remind you of something that we saw in the previous lecture? Just keep that in mind. We'll come back to that. Right. So this is what we got. V equals Vms by Km plus S, where Vm equals K3 into E total or Et, and Km is K2 plus K3 by K1. Now, does it strike you where you saw this earlier? If you plot V versus S, the rate of the reaction, the volumetric rate of the reaction with the substrate concentration, you get a rectangular parabola. Yes, it's the same form that we got for the Monod equation. The Monod equation gave us the variation of growth rate, the culture growth rate with substrate concentration. Here it is very different. Here it is the rate of the Michaelis-Menten enzyme reaction, the enzyme reaction which takes place in a Michaelis-Menten form with again the substrate concentration. The substrate concentration variation, that aspect is the same, but this is for an enzyme reaction, that is for growth kinetics. Okay, you must make a distinction between these two. People tend to confuse one with the other. So the same kind of, since it's the same form of the equation, the same kind of interpretations can be drawn. Vm is the maximum rate. I mean, the rate increases and then asymptotically attains the maximum rate Vm. And if we replace Km with S, then we get V equals S by 2S, therefore Vm by 2. Therefore, Km is nothing but the substrate concentration at which we get the half maximal rate, same as the Monod equation interpretations. The model parameters Vm and Km, these are the two model parameters that we need to completely describe a simple enzyme kinetics. They can be determined by doing an experiment where we follow the substrate concentration with respect to time in a batch reactor. Okay, this experiment is done in a batch situation, batch reactor. We collect S versus T data, and if we do that, the Michaelis-Menten equation is V equals V max S by Km plus S. If we invert this equation, okay, take 1 by on both sides, we get 1 by V equals inversion of this Km plus S by Vms, and this can be written as this is a plus here, therefore Km by Vms plus S by Vms. Km by Vms becomes Km by Vm into 1 by S, and here the S cancels out, so you have 1 by V. Okay. So if you look at this as y equals mx plus c, if you take this as y, if you take this as x, you can call this as m, the slope, and c, the intercept. Okay. So if you plot 1 by v versus 1 by s from the S versus T data, you should get Km by Vm as the slope and 1 by Vm as the intercept. This is the way in which these model parameters are estimated. There are some issues associated with estimating it this way. Let's not get into that for the time being. Let's assume that the data is good and we have a good spread in the data and so on, that the outliers are not going to affect the value itself. That's the essential problem here, if you know what I'm talking about. If you don't know, don't worry about it. You'll have to be a little careful while using this. That you can learn later. A plot of 1 by V versus 1 by S, which is actually called the Lineweaver-Burk plot, gives us Km by Vm as the slope and 1 by Vm as the intercept. From S versus T data, calculate V using two successive data points of S and T for plotting. This is what you need to do, because we have substrate concentration versus time. Okay, the rate is delta S by delta T over that short interval. That's what we are approximating. Okay, and we assign that delta S by delta T to the midpoint of the time. That's how we need to do it. When we have the data, we need to use the complete set of data to get the required parameters. It's experimental data. So 1 by V versus 1 by S, you'll get a line like this. The y-intercept is 1 by Vm and the slope is Km by Vm. Other types of plots can also be used. Let's not get into that. You can look at any standard book on enzyme kinetics, including your textbook, and that will give you the other plots also. Now, let a problem be assigned. You can try this problem out. This requires the concepts that we just picked up. Just to summarize, we started this lecture 5 with examples of enzymes being used in the industry, industrial enzymes. And then we also said that an enzyme can be used in a bioreactor to form a product of interest, and that is what we are looking at in detail. We said that we need the kinetics of the enzyme reaction. We went through the derivation of the Michaelis-Menten equation, which has two parameters, Vm and Km. In form, it is very similar to the Monod equation, which describes the variation of growth rate with substrate concentration. Here it's a variation of enzyme volumetric rate with the substrate concentration. And then we also saw that we could find out Vm and Km from the data of substrate concentration with time variation from a batch system by using the Lineweaver-Burk plot. Now we'll use some of those concepts to address this closed-ended problem, to solve this closed-ended problem. Please try it out, and of course in the next lecture I will show you how to solve this. The question reads as follows: an industry scientist is studying a novel method of disposing a toxin that results from cell culture during the course of cultivation. The aim is to enhance cell yields through toxin reduction and medium recirculation. The toxin does not affect cell growth if its concentration is below 7.5 millimolar. The particular toxin she is studying, X, as she has a lot of secrecy requirements, can be broken down enzymatically using the enzyme E, again secret. The breakdown was studied at 30 degrees C at a pH of 7.2, and the following data was obtained under batch conditions. This is the variation of time with time of X. X is the substrate here, the breakdown of which we are studying. This gives 5 points. At time 0 it is 20 millimolar, time 10 it is 17.7 millimolar, and so on. Part A determine the Michaelis-Menten parameters for this enzymatic degradation, that's part A, and B, if the total enzyme concentration is tripled, what will the medium contain toxic levels of X after 30 minutes. Okay. I think this is a nice place to stop lecture 5. We will meet again in lecture 6. See you then.